Hello, 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 hello. Hello. So, hello everyone. So, today we start our fifth class on fundamentals of statistical thermodynamics. So, before jumping into the content of today's class, let me just quickly discuss about the things that we have covered in our last class. So, so as you know, in our last class, so we started our discussion from the concept of negative temperature. Okay. So how this concept is basically coming. So before explaining that, so let me first write out what is the distribution of Boltzmann distribution. Okay, so if let's suppose there are two states are there, and when there is one is excited state, get plus number of particles, and slower energy state, n minus number of particles. In that case, the distribution, particle distribution looks like this to the power u by 3. Okay, so this is the ratio of particle distribution. Okay. Okay. So now, if you take log on both the sides, you get log of 1 plus 5 minus 1 epsilon by kb3. Now from here, you can write it as epsilon by 3 of log of n minus by n plus. Okay. So this is the expression of T. So this expression basically comes from the distribution of particles from two different energy levels. Now, so the main highlight thing of this particular expression is that it depends upon the logarithm of this term. Okay. So if you somehow manage to attain a state where n minus is less than n plus, that means the lower state population is smaller than the upper state population. In that case, this long term, this long n minus by n plus, this whole term will become negative, right? And if you substitute this thing here, it will give temperature term also become negative. Okay. So this is the way. So as you can see, so if you somehow at negative temperature, if you somehow want to attain, so in that case, you have to distribute the particles in such a way that the higher excited state should have larger fraction of particle compared to the lower energy state. Okay. And so theoretically, you can basically derive all the statistical thermodynamic quantities that we have knew till this time in the for the concept of this negative temperature. Okay. And also from third law, actually using third law, so how to achieve this basically very low temperature, how to do that? So for in order to do that, you know that from third law you can basically uh, reach this absolute zero temperature, not in a finite number of states. Okay. So because of that, what you can do is that we have discussed the process. So we have discussed the process in the context of spin particles. Okay, so we know the spin particles have two types of orientation. Either it's in up state or it's down state. Okay. So if you plot the entropy versus temperature diagram for a unmagnetized spin system or demagnetized spin system, this temperature versus the entropy behave like this. Compared to this, for a unmagnetic, uh, this is the magnetized one, and for unmagnetized one, the entropy versus temperature graph looks like this. Okay. So now, what you can do, you can move back and forth between these two curves by using this particular type of step jump. So like from here to here, then here to here, then again here to here, then again here to here, then again here to here. So by doing this for a very large number of times, so this process is known as, from A to B, known as isothermal magnetization. And this process is known as adiabatic demagnetization. Adiabatic demagnetization. See, if you do these two processes again and again, in that case, after a certain amount of time, you will basically able to manage to attain a very low temperature. Okay. So this is a possible way. So experimentally also this process you will achieve very less magnitude of temperature. Uh, Next we have calculated the different thermodynamic quantities like internal energy, entropy, and as well as the partition function for a two-level system. Okay, so what was the result? So results were like this. So for a two-level system, with let's suppose each of the state has a single degeneracy. So in that case, the partition function will looks like this. Okay. So the partition function looks like this, equal to 1 plus 2 epsilon by kb. Now, so if you plot the Q at different ranges of temperature, like T tends to 0, T tends to infinite, T tends to -0, but T tends to minus infinite. So all of these four possible cases, if you plot the partition function Q, for this particular two-level system, it looks like this. This is actually 1. This temperature. This is 2. And this side we are having uh, partition function Q, and this side we are having the temperature. The temperature is like this. This side is -10, -5, 0, +5, +10. And this side it's decreasing. Okay. It's at temperature. So the partition function looks like this. Okay, so there is a discontinuity, as you can see easily, and at T equal to 0 Kelvin. So and the next thing also that I've calculated is the internal energy. Okay, so internal energy. So we know that we previously knew the internal energy formula, right, from our previous discussion. That is U minus N is equal to N by Q minus N by Q by del Q del beta at constant volume. Okay. So for U equal to e to the minus beta E, if you calculate the U minus U0, it will give you U minus U0 as N E divided by e to the power beta E plus 1. If you plot this, it looks like this. It will looks like this. Okay. So here also this is 0.5. So at t, if you see t is to minus infinite, and also for t tends to plus infinite, this internal energy basically converges towards the value 0.5. And for okay, and for this template, for this uh, for the case of temperature, if it moves from if it moves towards zero Kelvin from positive and negative direction, in that case it will try to move either at 0, internal energy as 0, or it will try to move from internal energy towards +1. Okay, so this axis it looks like this. So in this axis we will body kT by epsilon, and in this axis we will body internal energy U by Ne. Okay. So here also, just like previously for the case of entropy partition function, here also there is a massive discontinuity is there at the 0 Kelvin temperature. Next is the entropy. Okay, so entropy looks like this. The formula of entropy looks like this. So it's dependent upon both the internal energy plus the partition function. Okay, this is the expression of entropy. And so from here, if you calculate the entropy, it will give you like this value. So A by T by to the power beta E plus 1 plus N K ln 1 plus e to the power minus beta E. Okay, so this is the value. So if you, for this case, if you calculate the entropy for different for different limiting values, so the entropy behavior looks like this. So okay, this is the direction to change the entropy, and this is the direction to change the temperature. Okay, this 0 here 0 -5 -10. Okay, and entropy it's here it's 1, here it's 0.5. So like this. Okay. So here unlike the previous cases, here you can see the entropy is continuous. Actually, there is no discontinuity is there for equal to 0 Kelvin. So this is quite the behavior of three different thermodynamic properties for the case of a two-level system. Now, from this concept, we then move to the concept of the canonical ensemble, right? So, so what is basically the idea behind making this canonical ensemble? So, it's basically a statistical concept to calculate, to basically to define a system, and from there to calculate many kinds of statistical property of the system. So it's basically a tool or a theoretical concept, you can say. So what is the concept? So the concept is like that. So in order to basically uh, create this canonical ensemble, we first need a closed system of specific volume, composition, and temperature. Okay, then we replicate the system with n times. Okay. So if you do that, you will get the same system with exact NVT, but n numbers of replica of the same system. Okay. Now, this the main features of this the members of this ensemble is that they are thermally connected with each other. So that means each member of this ensembles can basically interact via transferring the energy. Okay. So so for this ensemble, that in that case, you can what you can do is that since there are n numbers of systems or n numbers of members are there inside the ensemble, and let's suppose in zero, so since they are basically changing the energy between themselves, I mean interacting the energy, exchanging the energy between themselves, so that means their individual energy is not fixed, right, at a particular value. Although the total energy of the ensemble is fixed, if you basically add the energies and the corresponding number of system that has the same energy, if you multiply them and add among all the members, you will get a fixed energy value. So that means the total energy of the ensemble is fixed. But what you can do here is that, let's suppose in zero number of systems or members as E0 energy. So now N1 has E1 energy. Okay. So like that, if you calculate the weight of the distribution like this, n factorial by N0 factorial N1 factorial like this. Now from here, you can calculate the how this all the members of the inside the ensemble is distributed. If you follow the same Boltzmann distribution that was there for the case of partition function that we've discussed in the last couple of classes. So here Q is the total partition function we call. It's not a system particle function, it's a partition function of the whole ensemble. Okay. So that's why denoting it Q. The previous case for a system, particular system partition function, we are denoting it by small q. Now where is a capital Q. So now from here, from here you can calculate the internal energy of the whole. So if you get the hands on the total partition function of the ensemble, from here itself you can calculate the internal energy. This formula is same: U minus U0 equal to minus del log Q by del beta constant B. You can also calculate the entropy. Same formula is equal to Q minus U0 by T plus A into log Q. Okay. So these are the pretty much things that we have discussed in our previous classes. Now we'll move on to some new things that is the main topic of discussion for today's class. But before that, let us solve some problems. Okay. So first problem is system has three energy levels. 0 equal to 0, 1 equal to E, and 2 equal to D. The system is in thermal nuclear temperature T. So we have to find out find the partition function Q. B, find the probability of the system in each energy level. On option C. So on question is solved. Find average So we know this is the formula of the partition function Q. So so from here, first thing we have to calculate is a partition function, right? So there are three energy levels 0, E, and 2E. So Q would be to the power 0 plus E to the power beta E plus E to the power minus 2 beta E. So this is the expression of equal to 1 plus E to the power minus beta E and minus 2 beta E. So this is the expression of the partition function. Now from here, so you have to first, so this is the first quantity we have already calculated. The second thing that they are asking, finding the probability of finding each energy level. So there are three energy levels. So we know probability is basically related with n r by n. That is the EI probability. That is nothing but e to the power beta EI divided by Q. So for ground state P0 is to the power beta into 0 by Q, so 1 by Q. P1 it is e to the power beta E by Q, and P2 is e to the power 2 beta E by Q. So as you can see, so the probability of each of the states are proportional to the exponents of the exponential of the of that corresponding energy development. Also you can check out that. So E1 P0 plus P1 plus P2 gives you 1. Okay. In that case, all the probabilities are correctly normalized. Okay. So C is the average energy. So average of any quantity we know is basically energy of each of the level or each of the state multiplied with probability probability of the particle to be in that state. So EI into PI, probability to be at state basically. So P0 into V0 plus 6, there are 3 states at that, P1 plus P2 into 1. So P0 is 0, so P0 into 0. U1 is to the power beta E by Q into E1. Sorry, it's E, right? E1 is E basically. Plus Q2 is E to the power 2 beta E by Q into 2E. So from here, if you calculate it, it will give you Q, we know 1 plus E to the power beta E plus E to the power minus 2 beta E. In the numerator, you get E into E to the power minus beta E plus 2E into E to the power minus beta E. It is the average energy of it. You will get the average energy. Okay, so you get the probability, you get the average energy, you get the partition function. So this is the, we have solved all the question of this problem. The next problem will give now. So basically the next problem is a continuation of the previous problem. So for the problem of derive the internal energy U using the partition function. So the thing is, we already know the partition function expression, so you have to plug it in into the formula for deriving the internal energy, and from there itself we get the expression of the internal energy of the system. So we know the internal energy formula, that is minus E is equal to minus del log E by del beta. Del log, you can write it like this: 1 by Q into del 2 del beta also, right? So Q we know is 1 plus E to the power mod of beta E plus E to the power minus 2 beta E. So from here, if you substitute this thing here, you get U minus E is equal to minus 1 by Q into del beta of 1 plus E to the power minus beta E plus 1 plus minus 2 beta E. Do the derivative, will get minus of E to the power beta E plus, sorry, this of minus 2 to the power minus 2 beta E divided by Q. So now minus will become plus, it will give you. So this is E also here. So E into 2 to the power minus beta E plus 3 into 2 to the power minus 2 beta E divided by Q is 1 plus 2 to the power minus beta E plus 2 to the power minus 2 beta E. So this is the expression of the internal energy. So it's quite simple. You have to just use the expression of partition function, plug it into the expression of the internal energy that you have already derived in previous classes, and from there itself you get the expression of the internal energy. Okay. Next is problem 3. The problem 3, we have a system with two energy levels, so it will be very easier. But we will discuss some problems that is regarding calculating of different types of thermodynamic properties. Okay, so that's why I've chosen a easy system. So two energy levels, E0 equal to 0 and U1 equal to epsilon. Okay. So the system also has degeneracy. Okay. So the ground state has a degeneracy D0 equal to 2, while excited state has degeneracy G1 equal to 4. So the question is A, find the partition function option B, find the probability of being in the excited energy level, and option C, find the average energy. So here the partition function Q is given by summation over I Ci to the power minus beta Ei. So Gi is 2 into e to the power minus beta into 0 plus 4 into e to the power beta epsilon. Okay, so it will give you 2 plus 4 into e to the power minus beta. This is the expression of the partition function Q. Okay, so now from here, so you get the partition function. It is the first question. Now the second question B. You have to find out the probability being in the excited energy level. So the probabilities, we already know the formulas, right? EI is Ni by N, that is equal to Gi. So since here the degeneracy is involved, so to express Gi here, so Gi into e to the power minus beta E by Q. Excited state, that means at G1. Okay, so E1 would be G1 into to the power beta in 1 by Q. So G1 is basically 4, right? Yeah, 4 degenerate excited state, 4 into the power minus beta. The energy level of that particular level is E. Okay, E, yes. So E divided by Q. Q is nothing but Q plus 4 into the power minus beta E. So term writing like this, we can cut 2 from numerator denominator. Because beta E divided by 2, sorry, 1 plus 2 to the power minus beta. So this is the probability P. Okay, so you got the probability P1. So next thing that we have to yeah, so next thing that we have to calculate is the okay, so now we should be calculating so P1 and calculate. Now we have to calculate the average energy, right? So average energy is similarly EI into PI. So E1 into P1 plus E2 into P2. So E1 is 0, so 0 into P1, then you gives you 0. P1 is the energy is E into P2 is, sorry, it's E0, E0, P1, the mouse P1 into P1. P1 we know, it's 2 into 2 to the power minus beta E into 1 plus 2 to the power minus beta E, and E1 is E. So the average energy is equal to E 2 e into to the power minus beta E divided by 1 plus e to the 3 to the power minus beta E. This is the average energy level, okay. Average energy value. So the problem C is so this is done. So this is the problem C. Next that we have to calculate is some different quantity, that is find the heat capacity for problem 3. Okay, so for this 3 values problem, now we have to find out the heat capacity. Okay, so Q we already discussed is 1 plus e to the power minus beta E. Next thing that we have to calculate is CV. So the CV, the specific heat, has this particular form. We know the formula of specific heat. CV is basically GU by GT. Okay. At constant volume, but U is the internal energy. Okay. And no, it's but please okay. So from previous discussion, we know that U minus U0 we got as equal to epsilon e to the power minus beta E divided by 1 plus e to the power Now we can write this expression in a simpler way. We can multiply to the power plus beta I on numerator and denominator both sides. Then you will get u minus e to the s e divided by e to the power beta e plus 1. This is u minus 1. Now if you substitute this thing here, you will get C is equal to du by dt du by dt. If you put the derivative, it will give you epsilon to the power beta e plus 1. Take the derivative. Beta we know is 1 by kbt, right? It will give you minus epsilon square e to the power beta e whole square plus c. Here, in order to do that, we can also use this quantity also. So, d beta by dt equal to minus 1 by kbt square. This is du by d beta. So now from here, uh, Cv you can write it as du by d beta into d beta by dt, right? So du d beta we know this is the thing, and d beta by dt is this. So if you substitute these two things, you will get the Cv as e square by kb p square into e to the power beta e divided by 1 plus e to the power beta e whole square. So kbt you can also write it as beta, right? So in that case, Cv will become kb beta e whole square into e to the power beta e 1 plus e to the power beta e whole square. So this is the expression of Cv, the specific heat at constant volume. So these are some of the problems. So the main thing is that, or in order to the main summary that you can take from solving all of this problem is that for a system with like n numbers of energy levels, the first thing that you need to calculate, so this is for the case of single particle here, so it is easier to do that, is the partition function. Okay, so partition function general formula is this energy state and the degeneracy associated with each of the energy state, just add them, you will get the partition function. So if you need a partition function, you calculate the probability, you can calculate the internal energy, and from the internal you can calculate the Cv. Also the entropy also you can calculate from all of these quantities. So using the expression of all of these quantities. Okay. Now Now we will start our discussion on first. So till now, from last class, we discussed the partition function of the whole entropy, whole ensemble, right? But how this partition function of the whole ensemble is related to the single particle partition function. So that relation we will be going to discuss right now. So the topic is particle Q from canonical partition function of del Q. Now, as we know that in a canonical partition function, each of the members of that partition function of the system that is basically the members of the inside the ensemble. We know they are thermal contact with each other, so that means they are basically exchanging energy. So that means the each of the independent systems or members in the ensemble will not have the same energy level. Okay, might not have the same energy values. Okay, so for a particular system, for a particular member, the total energy of n molecules is basically sum of energies of the molecule. Okay, just add the energies one by one for each of the molecules. uh, for a particular system we'll get the total energy. Okay, now the total energy, let's suppose, so total, that means in mathematical way it looks like this. So for a ith member, let's suppose, or a particular member is in ith state or in ith state, whatever way, the EI is EI1, EI2, EI3. So like this, the total energy is like this. So EI1 is basically energy of molecule 1, EI2 is basically energy of molecule 2, provided the condition is that the system itself is in ith state. Okay, and EI is the total energy of the ith system. Okay, so now okay, now from here, uh, the total partition function can be written as q equal to the ensemble partition function, canonical ensemble, q equal to the power beta to the minus beta ei. Okay, so ei is basically the energy state of each of the member of the ensemble, right? So it looks like this: summation over I to the power beta e1 1 plus, sorry, minus, no, I take the minus is common, so plus e to the power beta ei2 plus root of e to the power beta ei n. Okay, now what you can do is that now you can write this thing like this, right? Q equal to summation over e to the power beta ei1 summation over ei2, like this. Now if you calculate this, so each of the term inside this grand partition function, as you can see, they can be denoted as q, small q. So small q is the partition function of each of the constituting systems. Okay, so yeah, so it can, the system, the system that is forming the ensemble, each of the systems, so they can basically take any type of energy values, right? So that's why the summation is taken over all possible values of ei. So if you do so, so each of the summation give you q, so there would be n numbers of q would be there, so it would be q to the power n. Q is capital Q. That is the ensemble partition function. And there is also so this is the case for distinguishable independent particles. You can basically distinguish each of the particles. Okay, you can whether some marker or something is there from which you can basically identify which particle is what. So in that case, for this indistinguishable particle, q is equal to q to the power n by n factorial. Okay, so there is a extra n by n factorial term is there. So this is for so first one is for distinguishable, the second one is for indistinguishable particles. Okay, next thing that we're going to discuss is the internal energy. So first, okay, so before going there, let me just briefly give an overview what is the meaning of distinguishability and indistinguishability. So the molecules, if the molecules to be that means they must be same kind. Okay, they are in same kind. Okay, like argon, neon. So those are the particles that are indistinguishable, and identical particle distinguishable. The opposite. You can basically distinguish each of the particles, okay, depending upon maybe their site, while they are on, or their charges or something like that. Some metric is there. From measuring that thing, basically get whether the particles is distinguishable or not indistinguishable. Next is so identical particle doesn't mean that they are indistinguishable. Okay, identical particle means it's like all the particles have identical properties. Okay, so that's why they are called as identical particle. That doesn't mean any distinguishability or indistinguishability. It can be distinguishable or it can be indistinguishable. Okay. Okay, now next the thing that we will calculate is the internal energy. Okay, internal energy. So first case we will calculate for distinguishable particle, then we calculate for indistinguishable particle, and last we will calculate for a monoatomic gas. Okay. So for a distinguishable particle, we know Q the is Q to the power n, and U minus U0 is equal to minus 1 by Q del beta at V. This is minus del of ln Q by del beta at constant V. Okay, yeah. So now from here, so Q you have to substitute this thing here. So if you do that, U minus U0 will get minus 1 by Qn into del Q to the power n del beta at V, 1 by Qn into n into Qn minus 1 into del Q del beta at constant V. So from here, U minus U0 will get minus 1 by Qn into n into Qn by Q del beta at constant volume V. From here, U minus U0 will get minus n by Q del beta at constant V. So this is the expression of the internal energy. Okay, for a for indistinguishable particle. Okay, so This is how the from the definition of the canonical partition function Q, capital Q, you will get the same expression in terms of the molecular particle partition function small q. Okay. Next is the for this is for distinguishable particle. Next is for indistinguishable particle. So for indistinguishable particle, we know it is one by q del q by del beta at constant volume. Okay. Minus del ln q by del beta at constant volume. U minus u0. Now this is for indistinguishable particle. For indistinguishable particle, we know q is q to the power n by n factorial. So now if you substitute this thing here, it will give you q minus u0 equal to minus q. If you substitute here, it will give you n factorial by q to the power n del q to the power n by n factorial del beta constant volume. N factorial by q to the power n by 1 by n factorial so this you will get after doing the derivative. So u minus u0 is this. So basically del qn by qn factorial, so you do the derivative with respect to qn, right? So qn has the beta thing inside it. So yeah, so if you do the derivative, now this thing will cut this here also some quantities. So some term will survive. So from here you can write it as n by q into del q by del beta at constant v. Okay. Minus. So as you can see, for both the cases, surprisingly, you get the similar value of internal energy. Okay, so for the case of distinguishable as well as for the case of indistinguishable particles, as you can see, the internal energy expression remains same. The next thing that we want to calculate is the entropy. Okay, so entropy of the monotonic gas. Okay. So we'll basically consider these particles as a monoatomic gas, and since it's monoatomic ideal gas we are considering, so that means they are basically indistinguishable. You cannot distinguish from particle 1 to particle 2. So yeah, so for that consideration, so first what we will write is the expression of the entropy, so that we know equal to S equal to U minus U0 divided by T plus K into ln Q. That we know the expression of the entropy. Now from here we know Q is the partition function, since we are considering monatomic gas and the particles are ideal particles with indistinguishability. So U would be q to the power n by n factorial Now from here, if you substitute these things here, you'll get S equal to Q minus U0 by T plus K of ln Q to the power n minus K of ln n factorial. From here you'll get S equal to U minus U0 by T plus Nk of ln Q minus K of, so ln n factorial you can use Stirling approximation since the n is very high, the number of particles, so these values are very high, so it would be n ln n factorial would be n into ln n minus n u minus u0 by t plus nk ln q plus nk. So S is this. Now from here we'll use the some of the relations from, since it's a monatomic gas, we'll ideal monatomic gas, so we will use some relation from the ideal gas law. So first is Nk. So N is the number of particles in the K, right? K is the ideal gas constant. So this thing can write it as N into Na, Avogadro number into K. So Na into K is R. So Nr can write. So Nk, we can replace Nk by Nr. N is small n is the mole number. Okay. U minus U0 by T plus this is Nk. So Nk we can write it Nr ln Q minus Nr ln n plus Nr. Now we can further simplify it more. So AS is basically 3 by 2, and yeah, so U minus U0. So for ideal gas, we know the internal energy expression U minus U0 is 3 by 2 nRT, right? So we'll substitute this thing here. Okay. After doing that, you will get the expression of entropy as 3 by 2 nRT by T plus nr into ln of Q plus minus nr into ln n plus nr. So from here tt will cancel, so you'll get 3 by 2 nr plus nr into ln Q minus nr into ln n plus nr. So 3 by 2 nr plus nr will give you 5 by 2 nr plus nr into ln Q minus nr into ln n. This is the entropy S. Now since so there are so out of three quantities here in the expression of entropy S, so two of them are in logarithmic term, right? But if you can write the third term also in terms of logarithmic term, then you can basically add them up and like squeeze all these three quantities into a single quantity, right? So to do that, we will write this thing as this 5 by 2 as nr into ln of e to the power 5 by 2 plus nr into ln of q minus nr into ln of n. Okay, so now all the three quantities are in logarithmic term right now. So we can further simplify it and write it like this: ln of e to the power 5 by 2 q divided by n. Okay, so q, you know, q is the, on the very first class we have calculated the value of q for a gas, for ideal gas that is trapped, that can be freely moved inside a box, sort of a box. So q was the for those kind of system is v by lambda q, right? But lambda discuss is nothing but thermal wavelength, that is beta I square by 2 pi m. Okay, m is the mass, half, and v is the volume of the container where the gas is. Okay, enclosure, you can say enclosure. Okay, so this is the common expression, the general expression. So from here, nr is ln of, so to the power 5 by 2 v into, so n you can write is at n into na, the Avogadro number, by lambda cube. Yeah, so this is basically the expression of the entropy. Okay, for the case of a uh, monoatomic gas, monoatomic ideal gas. Okay, and this thing you can write it in different ways also. So you can also write it in terms of pressure. So here you can see you have written in terms of volume. So we know PV equal to nRT, right? So V by N you can write it as RT by P. Okay, so in that case this whole expression you can write is equal to, if you substitute this thing here, you can write this as nr into ln to the power 5 by 2 V by N would be KT by P, sorry, RT by P, yeah, RT by P in by Na into lambda cube. And we know that Na by K into R, so Na into K is R, so R by Na is basically K, that means the ideal gas, the yeah, the Boltzmann constant. So R by so this R by Na will become K, so e to the power 5 by 2 into KT by P into lambda Q. Okay, so this is the expression of the entropy we got. So this, the first expression is in terms of volume, we got the expression of entropy. The second, we got the entropy expression in terms of pressure. Okay, and this equation is, there's a name of this equation, that is known as this Sackur tetrode equation. Okay, it is known as Sackur tetrode equation. It's a very useful equation. Using this you can calculate the entropy of systems basically. Now one of the important feature of this Sackur tetrode equation is this. You can use the molar entropy. So we can define the molar entropy here. Okay, so using this so using this equation you can calculate the molar entropy. Molar entropy is nothing but entropy divided by mole. Okay, so it will be R into ln of e to the power 5 by 2 KT by P by lambda, or in terms of V, whatever. So by using just by using the pressure and temperature of the gas, you can calculate the entropy, the molar entropy specifically of the system. Now we'll do some problems on it. Find the standard molar entropy of the gases helium at 25 degrees centigrade. Temperature is given T equal to 298.15 Kelvin. P is equal to 1 bar, that is 10 to the power 5 Pascal, and molar mass same, helium is 4.002602, atomic mass, that is U. Okay, so the expression we know, the entropy is S, molar entropy SM is basically R into ln of e to the power 5 by 2. So here the pressure is given, so we'll use the formula that involve pressure in it, kT by P 0 into lambda q. So lambda thing we have to first need to calculate, right? So so molar mass is given, so for molar mass we have to calculate the, yeah, so from the molar mass you have to calculate the atomic mass. Okay, so so to do that, so what you will do, so mass would be first, so there are a couple of, the mass would be basically molar mass, that is m divided by Na. Okay, that is given here as 4.002602 U. Okay, the next thing that you have to calculate is lambda. Lambda we know is a very big quantity, h by 2 pi m kVt. So I have to just substitute the values here. So lambda is, h we know 6.626 into 10 to the power minus 34. 2 pi is 2 into pi into m. So m is the mass, atomic mass. You have to convert atomic mass into kg. You have to, what you have to do, you have to multiply uh, multiply this with the mass of a proton in kg. So if you multiply that, you'll get m as 6.6465 into 10 to the power minus 27 kg. So this thing you have to substitute here, 6.6465 into 10 to the power minus 27 into 1.38 into 10 to the power minus 23 into 298.15. Lambda, if you calculate it, it will give you 5.05 into 10 to the power minus 11 meter. Okay, and entropy, S is equal to ln e to the power 5 by 2. Now just substitute the things, right? So k we know 1.38 into 10 to the minus 23 into 298.15 divided by 10 to the power 5 into 5.05 into 10 to the minus 11 whole cube. So calculate it, entropy, it will give you 126.2 joule mole inverse Kelvin inverse. Okay, so this is the value of entropy you'll get. Okay, Now next we will discuss some of the more features of this Sacco-Tetrode equation. So the equation is, let me write it again in terms of volume, is equal to nr into ln of e to the power 5 by 2 into v n into na lambda q. Okay, now so this whole thing, so most of these things are constant. The only thing that has temperature, that has the parameter involved is lambda. Okay, the lambda has 1 by square root relation with temperature. Okay, so if you make the temperature as constant, so that means this whole quantity that is multiplied with volume will become a constant. Okay, so at constant temperature we can write this entropy as nr into ln a v. So we basically taken up this whole quantity as a single constant a into this expression. So now it basically helps us to work with this equation in a easier fashion. So now what we can do is that we can calculate the entropy, change of entropy. Okay, so let's suppose the system changes its volume from Vf to Vi. So initially let's suppose the volume of a system was Vi. From here it changes to Vf. Okay, you basically expand, maybe. Okay, expanded to Vf. Okay, so in that case the change of entropy is delta is equal to nr. The only thing that can be changed, this thing is happening at constant t. Okay, this is an important assumption, otherwise this formula will not be valid here. So nr is ln a delta v, so it will become ln nr ln a, sorry, delta will be outside, vf minus nr ln a vi. Okay, this we can write nr ln vf by vi. Okay, and this thing is also consistent with the thermodynamic definition of entropy also. Okay, so from thermodynamic definition we know, let's just does the fact check. So d equal to dq plus dw, right? So for isothermal case, I mean the temperature fixed case, we know t is equal to 0 for isothermal, t constant case. So dq will become minus dw. So dq we know is tds equal to dw is pdv, that we can write it as nrt minus minus will become plus nrt by v into dv. So ds is basically nr v by dv. So if you integrate, you will get sorry, ds, so delta s equal to nr ln vf by vi. Okay, so that is a change in entropy for an ideal gas, which is consistent with the equation that we found through the Sacco-Tetrode form. Okay, that means the equation is consistent, whatever we get, I mean consistent with the thermodynamics of the system. Okay. So now we will do some problem regarding this. Okay. First problem is isobaric expansion. Okay. The problem one is on isobaric expansion. Okay. So what we'll basically do, the system is given at n equal to 1 mole, P remain constant since it's isobaric, volume changes from 5 liter to 20 liter for a monoatomic ideal gas. Calculate the change in entropy. Okay. The change in entropy formula we know delta S. Since your volume is only changing, so you know the formula, right? So NR ln P2 by V1 okay. So N is mole is how much? Mole is N mole. Okay, so N is 1, so 1 into ideal gas constant, that is 8.314 into ln of V2 by V1. Okay, so Vf is 20 and Vi is 5. So it will become 4. So delta S will become 1 into 8.314 into ln of 4. So it will give you around, 1 second. It will give you around 11.54. 11.54 joule Kelvin inverse mole inverse. Okay. This is the per molar change. Okay. The next problem is find delta S from the temperature change at constant P. Given n equal to 2 mole, T1 equal to 300 Kelvin, Ti equal to 300, Tf equal to 600 Kelvin. So that means here you have to calculate. So here, unlike the previous case where V remains constant, here P remains constant and T changes. Okay. So we cannot use the normal formula. So the normal formula is this: delta S is equal to NR ln V2 by V1. So since the temperature is changing but P remains constant, so through T basically V is changing. Okay, but we cannot readily determine what is the change in V. So I mean from the question. So PV equal to nRT, right? So uh, V is proportional to T, so that means V2 by V1 is equal to T2 by T1. Okay, at constant pressure, obviously, at constant pressure. Okay, so delta S is equal to NR ln of V2 by V1 is T2 by T1. So T2 by T1 is NR equal to into ln 600 by 300 equal to NR into ln of 2. So N is 2. So mole is 2 mole is there. 2 into R is 8.314 and ln 2. So do this. Here also if you do this, same type of answer. So so see here also, since like the previous cases, here also the change would be 11.54 joule per mole inverse Kelvin inverse. Okay, so the next problem number 3. System contains two independent subsystems with multiplicity W1 equal to 3 into 10 to the power 18 and W2 equal to 5 into 10 to the power 21. What is the multiplicity W of combined system? Compute S1, S2 and total entropy S, and C is So these are the two things only. Okay, answer. So yeah, so the system has two independent subsystem, and each of those two system has two different multiplicity. So multiplicity means number of states that are available there. Okay, number of possible states that can be associated with that particular system. Okay, I mean subsystem. So since these are two independent subsystems, so their multiplicity, total multiplicity will be multiplication of two different multiplicity, w1 into w2. W will be equal to w1 into w2. So it will become 3 into 10 to the power 18 into 5 into 10 to the power 21, give you 1.5 into 10 to the power 40. This is the total multiplicity. Now from here you can calculate the S. So S as kb ln w it should be kb ln w is so first we will calculate for S1. Okay, so S1 is kb ln w1. So w1 is 3 into 10 to the power 18. Okay, kb into ln 3 plus 18 into ln 10, right? So if you do that, you will get kb ln 3 is 1.09 plus 18 into 2.305. This gives you 5.87 into 10 to the minus 22 joule per Kelvin. Okay. Similarly, S2 also you can calculate. So S2 is kb ln of 5. So W2. So W2 is how much? 5 into 10 to the power 21. So kb equal to into ln of 5 into 10 to the power 21 kb into ln 5 plus 21 into ln 10. kb ln 5 is 1.609 plus 21 into 2.302 kb into 49.964 kb. We know, so kb we multiplied 49.964, you get 6.89824 into 10 to the power minus 22 joule per Kelvin. This is the expression of S2 you will get. So S1 and S2 you get. Now is the total entropy S. So S is kb ln 1.5 into 10 to the power 40. So kb ln of 1.5 plus 40 into ln 10 kb. So ln 1.5 gives you around 0.405. 40 into ln 10 gives you around 2.3025. So from here kb, so if you add this two, it will give you 92.509. kb into this gives you 1.277 into 10 to the minus 21 joule per Kelvin inverse. So this is the problem. So the main thing is that in this problem is that this AS so is you get 1.2722, right? Now this same AS you can get it by adding S1 plus S2 also. So S1 plus S2 gives you also around, if you add S1 plus S2, this also gives you around 1.27 into 10 to the power minus 21, which is S basically. So that means is that S we can write the total entropy is addition of two entropies. Okay. The main thing is that from here is that entropy is additive quantity. Okay. So if you, that means if you mix two systems, their entropy will not multiply with each other. Their entropy will add with each other. Okay. Entropy is additive for independent subsystems. Okay. Okay, fine. So next we'll now focus on the Helmholtz free energy. Okay. So that means we want to in the next section we want to find out the expression of pressure from the ST equation. ST equation means uh, the equation of the entropy and temperature. Okay. So so the pressure. So before deriving into the pressure equation, we basically need the concept of Helmholtz free energy actually previously before that. So Helmholtz free energy A, this is the Helmholtz free energy. Okay. So A is defined as U internal energy minus T into S. Okay. So dA you can write it as du minus TdS minus S dt. Okay. And du you can write it as dq plus dw minus TdS minus S dt. So dA dq you can write it as TdS plus my dw you can write it as minus PdV minus TdS minus S dt. So TdS will cancel to give you minus PdV minus S dt. Okay. So now, so that means from this relation of dA, can write P as minus dA by del A by del V at constant T. So this is the useful relation that we are going to use. Okay. Now this is at constant temperature. Okay. So now from this relation A equal to U0 minus Ts. So from this relation at constant temperature we can write A minus A0 equal to U minus U0 minus Ts. Okay, temperature remain constant. So from here we can write A minus A0 equal to U minus U0. Ts we know, S expression we know, U minus U0 by T plus K of ln Q. Okay. Now from here you can write A minus A0 as minus KT ln Q. Okay. So this is the expression of, we can write it as delta I. Okay. Minus KT ln Q. So this expression of delta we can substitute back in this expression. After doing so you get P equal to kT ln Q by del V, del of ln Q by del V at constant T. So this is the expression of pressure that you can get from here. Okay, so now so this is the expression. So yeah, so now from here, if you substitute Q and all, so different, so that means this is very useful expression. So for a system, if you know the total partition function Q, from there itself you can basically calculate the pressure of the system. Okay, so we have previously calculated the how the internal energy, how the total energy, how the specific heat, how the entropy is calculated, the partition function. Now in the next here we have calculated how pressure is related to the partition function. Okay, so this is so this basically proves the fact that the partition function is really a very powerful quantity, and we can relate mode of this many thermodynamic function with this partition function. Okay, so yeah, so that's it for today's class. So